Afternoon. So I welcome you all to the problem solving session 3 for the NPTEL course Fluidization Engineering. So let us wait 2 more minutes for others to join. If not, we will continue with the session. I have made changes in the Google Meet so that anyone can join the meeting. So if you people are thinking to join, you can join. So the session is open actually, and we'll wait 2 more minutes and start the session by 3:05. In the meantime, if you people have any doubts regarding the last week session, that is problem solving session 2, you people can ask, or else we'll start with today's session. So before going to the session, since in the time we are waiting for others to join, we can I can introduce myself. So myself, I am Ankara Kartika from IIT Hyderabad. So I am working on fluidization. So as part of my project, so I can help you in understanding and solving problems related to this particular course. So you people can ask any questions related to the course, so I'll be happy to take those questions and answer them for you. So just for your information, this session is being recorded. So well, we'll start. If there are people, they can join. So let me start again. I am Ankara from IIT Hyderabad. So I am the TA for this course, like where I'll be solving the problems related to that week's assignment, and based on that, you people can solve the assignments and submit it on time, so that, as you people know, the assignments carry certain weightage in the final exam marks, the final marks along with the final exam. So please submit the assignments on time, and if you people have any doubts regarding problems, I may not be able to provide direct answers, but I'll be giving you any other help required. So yeah, so this course is Fluidization Engineering. So the course code is this NOC 24CH57, and the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. So now currently we are at problem solving session 3, and the session will be from 3 p.m. to 5 p.m. So we'll move to the course. So as we all know that this particular fluidization engineering is a 12-week course. So each week you will be having lectures from the professor, and based on that there will be assignments. So you people have to submit the assignments on time. This week assignment 2 submission was over, and from next week assignment 3, assignment 4, everything will be starting. So in the last class we saw how to solve problems related to assignment 2, and in today's class I am also, in addition to problems related to week 3, i'll I'll also be solving assignment 2 problems from this particular session. So like if you have any doubts in those things as well, we can discuss and we'll be getting those things clarified. So that is the thing. And now we'll start with the course layout. I have discussed this other times also, so I'll just give you a brief introduction. So this is a 12-week course. In the first few weeks, we are just dealing with the introduction to the fluidization and advantages and disadvantages of fluidized beds and industrial applications of fluidized beds. Also how solid classification is being handled and flow characteristics and its outline in different types of fluidization. So from I hope from till now you will be having a very good knowledge on what is fluidized beds. I mean, what are fluidized beds. So and why we are using. So those things I think you'll be having a very good idea as of now. So in the week 3 we'll be dealing with characteristics of solids. So in last classes itself we have seen that solids are mm, playing a major role in the flow behavior inside the system based on their size, density and the shape factor is also an important one. So like one basic classification is given by Geldat in 1974, where he classified the powders into four groups A, B, and C and D. So C is cohesive particles, A is C is the smallest size particles, and A is slightly larger, and B is slightly larger, similar to the size of sand, and D is very large size particles. These Geldat classified the particles based on their size as well as the density. More to say relative density between the fluid and the between the particle and the fluid. So those things and flow characteristics and its outline in different types of fluidization. So inside the fluidized bed, based on the fluid flow velocity, that is fluid inlet velocity, the flow characteristics vary. So those things are also given over here. And in later weeks we'll be seeing about the flow pattern transition, flow pattern of mapping, and frictional pressure drop, models required to analyze them, solid movements, mixing, segregation, all those phenomena like mixing, segregation. These things happen based on the velocity also of the fluid, velocity of the fluid. So at low velocity there may be segregation, and at higher velocity there may be complete mixing, promoting mixing would be there. Those things would be we'll be dealing. And later on we'll be moving on to design aspects like gas distributor. Gas distributor is nothing but we have particles packed in the packed bed. From the bottom we'll be passing fluid, and that fluid passage will be through a distributor. And later the important phenomena of bubbling fluidized beds will be dealing with. Bubbling fluidized beds are nothing but in if we pass gas inside the packing, those particles at starts to move at a higher velocity. We'll be starting to observe the formation of bubbles, and later on we'll be dealing with elytration and entrainment from fluidized beds, where solid particles might be escaping from the top of the bed, and we need to recover them and pass them again. And attrition is the behavior, it's the phenomena when two particles rubbing against each other and there may be loss of material. And then last few weeks we'll be dealing with mass transfer and heat transfer phenomena happening inside the fluidized bed. So these are all common aspects. So right now we'll be seeing the books and references. So the first one is Cooney and Levinspill's Fluidization Engineering, and second one is Multiphase Flow and Fluidization by Gidaspo. Third one is Fluidization Dynamics, and fourth one is K Majumder's Hydrodynamics and Transport Processes of Inverse Bubbly Flow. So in last two classes itself I gave enough introduction about the books and references of what type of books would be very useful and what these books are covering. So if you want to have an idea, go check out the last videos. Now we'll move to fluidization. So I don't want to jump in directly into the problems, even though you people have an idea of what fluidization is. I just want to give an introduction. That is because fluidization may not be a common concept to every chemical engineer. This is not like thing that you would be completely aware of. You might have studied it as a part of a subject in part of your subject in your BTech, but generally you like it is like a specialization. So now just to give you an introduction of what is fluidization. Fluidization is nothing but in general we deal with packed beds in industries, right? Just give me a minute. So yeah, we'll be seeing now. Fluidization is nothing but we have a system with packed particles inside the bed, and we pass air through the bottom. This is what I call it as a distributor. So when initially the bed would be packed such that, consider this as a packed bed. So initially inside the packed bed, this complete thing would be solids, and there would be no space for the solids to move even though we pass on the liquid, I mean fluid. I mean, to make it more clear, we have a packed bed of particles. I'll just rub these things. Okay, let us forget everything and we'll start fresh. So what is fluidized beds? Fluidized beds are nothing but wherein we pass the fluid inside the solid packed bed, and those particles starts to behave like a fluid, that is they start to move. When will this happen? When we are passing the fluid at a sufficiently higher velocity. At low velocity the particles would not be moving, whereas at higher velocity those particles would be moving. So to say clearly, consider this is a packed bed. So here we have solids packed till here, and we allow the fluid from here. So in packed bed condition, these particles would be packed till this height, means they would be available only till this height. And with increase in velocity, those particles would not be starting to move. Whereas in fluidized bed, these particles would be moving out, not exactly out of the bed, but these particles would be like fluidizing. That is what we call it as a fluidized bed. So what would be the definition of fluidized bed? Fluidized beds are nothing but when we pass the fluid inside the bed at a sufficiently higher velocity, and those particles would start behaving like a fluid than having the solids behavior. So this happens only at a sufficiently higher velocity. So before that velocity the bed would remain as packed bed. After that velocity the bed would remain as fluidized bed. So that is the basic difference. So what happens in terms of forces? So in packed bed the drag force is less than the gravitational force. Drag force is nothing but the force exerted by the fluid on the particle, which is pulling the particle along with it. Whereas the gravitational force is very much higher in the packed bed. The velocity with which the fluid is pulling the particle is not sufficiently high. So the drag force is less than the gravitational force. So the particle remains in the packed condition and they would not be moving at all. So we call it as a packed bed. Thus, when we increase the velocity at a certain point, the weight of the particles inside the fluid is bed, particles on the fluid would be balanced by the pressure drop or something. So at that condition we call it as minimum fluidization condition. The bed would remain in the loosest possible packed state. like the bed would not be, particles would not be moving, whereas the particles would not even be closely packed. So that is the point at which the bed would be uh, known as incipiently fluidized bed, or at the bed is at the minimum fluidization condition. So after minimum fluidization condition, the bed is known as fluidized beds, whereas below minimum fluidization condition, the bed is known as packed bed. So this variation of the bed from packed bed to fluidized bed happens because of the increase in the fluid velocity. So this is the fluidized bed. As we can see, the voidage inside the bed increases in the fluidized bed compared to the packed bed. In packed bed, the voidage is lower than in the fluidized beds. So as we can see, there is interstitial air with more volume comparatively, which can be found in the packed bed. So this is the fluidization concept and fluidization regimes. So with increase in velocity, we have seen that the fluidized beds is being obtained. So there are, at with certain increase in velocity, we can observe different behavior inside the fluidized beds. So that is what is shown over here. We call it as a fluidization regimes. So if this is known as packed bed, as you can see, the bed height remains the same. How much ever we increase the fluid velocity, that is gas or liquid, that is low velocity, the bed remains the packed bed or fixed bed. After that, we are increasing the velocity and we are able to observe that the bed remains in the loosest possible packed state, and this is known as minimum fluidization condition. So after minimum fluidization condition, the liquid inside the fluidized bed and the solids inside the fluidized bed starts to behave differently. So if we pass liquid, we have a smooth fluidization. As you can see, the particles are increasing in height inside the bed and the bed height is increasing, but we are not able to see any bubble formation over here. So this happens in case of liquid fluidized beds or at a very low gas velocity. But in general, if we increase the fluidizing gas velocity, we are able to see the formation of bubbles. And with increase in the velocity further and with diameter of the column, we are able to see that the bubble size grows in size and it is almost occupying the size of the column. So this is known as slugging beds. So if bubble size is almost the size of the column, we call it axial slugs, and if bubble size is has reached the size of the column, we call it flat slugs. And after slugging, even with if we are further increasing the fluid velocity, we call it turbulent fluidization, because the bubbles starts to break when they reach the surface of the bed and they pop out the solids, and it would be recirculation will be taking place over here. Over here, like there would be movement of solids to the above surface and they would be pushed down. So after that, with further increase in the velocity, we are able to see the particles would be escaping the bed, and it is known as lean phase fluidization with pneumatic transport. The solid particles are being transported over here. So this is fluidization regime. So this week 3 course is mostly situated around fluidization regime. So now we'll go to the problems. So the first one is multiphase behavior is not affected by option A, interfacial. Okay, I'll just put animation so we can discuss. So now we are going to question 1. In question 1, the question is multiphase behavior is not affected by option A, interfacial surface tension force, and option B, it is wetting characteristics of liquid on the channel wall, option C, surface area, option D, contact angle. So if you any one of you have answers to offer, you can do that, or we'll discuss the answer also in a minute time. So the answer is surface area. As you people would have seen from the options, option C, surface area is the right answer. Why? Because multiphase flow behavior, if we say that, what does it mean? It is meaning that gas solid or liquid solid or gas liquid solid, all those phases are inside the system, and how or what are the factors that would be affecting the multiphase behavior. The option 1 is interfacial tension force. So obviously the interfacial tension between the particles in the fluid would be playing a major role. And second is betting characteristics of the liquid on the channel wall. Again, the channel wall is like a different phase and the liquid is a different phase, and based on that these particles, I mean these liquid might be sticking to the wall. So and we need to account that as well. So wetting characteristics of the liquid on the channel wall. And third is surface area. Although like with increase in surface area, the chemical reaction or those things would be affected, the multiphase flow behavior as such should not be enhanced. Like because of the increased surface area formed during the fluidized beds, we can say that all other properties are getting improved, but the flow behavior inside the system is not being affected much by the surface area. The last one is contact angle. However, the contact angle also plays a major role. So right answer to this particular question is surface area. And question 2, in question 2 it is given that in a fluidized bed the flow regime of multiphase flow depends on which factor. So here the question is about fluidized bed. In fluidized bed the multiphase flow regime depends on which factors. So it is similar to the last question, and the first one is geometric variables, and second one is thermodynamic variables, and third one is physical properties of the phases, and last one is all of these. So in fluidized beds, flow regime of multiphase flow depends on which factors. So pick out one answer and we'll discuss why. If anyone wants to answer, please unmute yourself and you can answer. So yeah, well, all of the above is the right answer because it is a simple question. We can say that. Why? Because dynamic geometric variable is like the geometry of the system, or like the distributed design, everything. And circular fluidized beds or rectangular fluidized beds, all those things would be uh, playing a role in terms of flow regime of multiphase flows. Second one is thermodynamic variables. Thermodynamic variables is nothing but based on the temperature of the systems, those things also will be playing a role. Physical properties of the phases, again this would be playing a role. So the right answer to this particular question is all of these is the right answer. Option D is the right answer. So in question 3, we'll move on to question 3. In question 3, the most unstable condition corresponds to transition from bubbling to turbulent fluidization based on changing dash. So we'll look at the option first. Option A, top surface of the bed. Option B, bundle of slugs. Option C, velocity. Option D, surface area of the bed. So I'll give you guys 1 minute time. So in that time, I want you people to come up with what is the right answer and why is that the right answer. So what is asked in the question? In the question it is asked that the most unstable condition corresponds to transition from bubbling to turbulent fluidization based on changing dash. So we'll just divide the question into three parts and then we'll be able to find out the right answer. The most unstable condition. Here the question is regarding most unstable condition and it is corresponding to the transition from bubbling to turbulent fluidization. So when the bed is transitioning from bubbling to turbulent fluidization, there is an onset of unstable condition and that occurs when. So if there is a transition from bubbling to turbulent fluidization, it results in an unstable condition. Okay. So what results in the transition from bubbling to turbulent fluidization is the question. So it is a very straightforward question because in the last few slides before only we have seen that how fluidization regime is varying from. Okay. Fluidization regimes are varying from fixed bed to bubbling fluidization when we are dealing with gas, like after the minimum fluidization condition. So when does this happen? This happens when we increase the gas or the liquid velocity. That is when we increase the fluid velocity. So we are able to see the bubbling fluidization. After that, in this particular question, what is being asked? It is asked regarding the transition from bubbling to turbulent fluidization. So this again happens with increase in velocity as we all know. So all these things from left to right, the transition happening because we are increasing the inlet fluid velocity. So inlet fluid velocity is very important factor that is influencing the flow transition behavior of the system. So we'll go to question 3. Now it will be more clear. The most unstable condition corresponds to transition from bubbling to turbulent fluidization based on changing dash. So what are we changing over there? We are changing the velocity of the inlet fluid. So options, we look at the options: top surface of the bed, bundle of slugs, option C velocity, option D surface area of the bed. So we know now that option C velocity is the right answer. So it is bed. So I am just changing that. I hope question 3 is clear to you people. Now we will go on to question 4. Transport phenomena, particles impact against each other or the bed wall takes place. So in which transport phenomena particles impact against each other or bed takes place? So here the question is regarding the transport phenomena. So like where in that particular transport phenomena what is happening, the particles are impacting against each other or even with the wall of the column or the bed is taking place. So that is happening in which transport phenomena is the question. So the first option is that strand transport and second one is dilute phase transport and option C it is plug phase transport. Option D, it is dune transport. So the transport phenomena is here is nothing but the four types of transport phenomena happening inside the pneumatic fluidization. So there are four transport phenomena. So the first one is given in the option as strand transport, second one dilute phase transport, third one plug transport, and option D dune transport. So the first one is strand transport. So here the first thing that is happening is that in dilute phase transport where the velocity is very low, and next is the strand transport, that is dilute phase transport. Next is the strand transport wherein the velocity is lower, and the dune transport wherein velocity is uh, I mean uh, lower. So velocity is in lower further, and we are able to see that plug flow or the blockage occurs at the last. So in the question it is asked that particles impact against each other or the bed wall takes place. So here the right answer is dilute phase transport. In dilute phase transport, line distributed evenly across the cross-sectional area and the particles impact against each other as well as the bed wall. So that happens in case of dilute phase transport. But apart from that, what is the order? The first one is suspension or dilute phase, and second one is strand transport, and third one is dense phase dune transport, and last one is dense phase plug transport. So these are the options, and from the option we are able to figure out the right answer as dilute phase transport. Option B is the right answer. Now let us move on to question 5. In question 5, it is asked that the fluidization where the bed does not expand much beyond its volume at minimum fluidization. So options are pneumatic conveying fluidization, option B fast fluidization, option C turbulent fluidization, option D spouted fluidization. So again we need to understand what the question is about. The question is about what type of bed does not expand much beyond its height, much beyond its volume at minimum fluidization. So here the bed size almost remains the constant. So from that itself we can eliminate few options from this particular set. So in the option A, it is pneumatic conveying fluidization. We all know that with a very high velocity that is happening inside the pneumatic system, the particles are getting transported out of the system. That is one thing, and because of that the volume is also getting affected. Option B, it is fast fluidization. The same case of argument holds over here also, because with increase in velocity from the bubbling to fast fluidization, we are able to see that the particles bed height has improved, and therefore it is changing beyond its value, and same is the case with turbulent fluidization. But what is spouted beds? Spouted beds are nothing but those that would not expand much beyond its volume at minimum fluidization condition. So here the key thing is at minimum fluidization condition. Spouted bed does not expand much beyond its volume at minimum fluidization condition. So answer to this particular question is option D. We'll now move on to question 6. In question 6, it is asked that at low slug regime, where U is the velocity of the fluid and UMS is the minimum slugging velocity, and UC is the velocity at the condition at which standard deviation of different pressure fluctuation reaches the maximum. So what is being asked? In the question it is clearly given that it is a slug flow regime, and if U we are dealing with in the option is velocity of the fluid, and UMS is the my minimum slugging velocity, and UC is the condition at which standard deviation of differential pressure fluctuation reaches a maximum. So now we are to identify which is the condition for the particular slug flow regime. So the first one is in slug flow regime, the velocity would be greater than minimum fluidization, minimum slugging velocity. So UMS is less than U, that is the velocity of the fluid. So UMS is greater than U, that is one option. So we'll look at the option first and then come back to discuss the answer. Option A, it is UC less than or equal to U less than UK. And second one is UMS less than or equal to U less than UC. And third one is 0 less than or equal to U less than UMF. And D, it is UMF less than or equal to U less than UMB. So what is the condition at which standard deviation of differential pressure fluctuation reaches a maximum? So in this condition for slug flow regime itself we can say that U is greater than UMS. So that particular thing is available only in option B, and it is less than UK or UC in this particular context. So the operating fluid regime, fluid value, fluid velocity should be greater than UMS, that is minimum slugging velocity, but less than the critical velocity at the condition at which model standard deviation of differential pressure fluctuation reaches a maximum. So option B is the right answer. We'll go to question 7. In question 7, it is asked that in bubbling fluidization, minimum bubbling velocity can be estimated from the correlation dash where dp is diameter of the particle, rho g is the gas velocity, and mu g is the gas viscosity. And the question is about finding the minimum bubbling velocity correlation from the correlation where the particle diameter is dp and gas viscosity is mu g and rho g is the gas density, and we need to find out the minimum bubbling velocity or minimum bubbling velocity formula. So given is dp mu g rho g, so we'll first look at the options. UMB, that is minimum bubbling velocity, is equal to 33 into dp into mu rho g by mu g power 0.33, and second one is UMB is equal to 33 dp rho g by mu g 0.5, and option C, it is the UMB is equal to 33 dp into rho g by mu g power zero point 0.1, and last option, it is UMB is equal to 33 dp and mu g by rho g 0.1. So answer to this particular question, I guess it should be C. UMB is equal to 33 dp rho g by mu g power zero point 0.1. So in this particular question, it is interesting to note that UMB is a function of diameter of the particle and density of gas and viscosity of gas. So it can be estimated from this particular correlation where UMB is equal to 33 into dp into rho g by mu g power 0.1. So does anyone remember who gave the expression for this particular formula? UMB is equal to 33 dp into rho g by mu g power 0.1. So that is the answer. And we'll go to question 8. In question 8, it is asked that during transition for pneumatic transport fluidization, transport line is determined by superficial gas velocity, relative velocity between gas and the particle, and at last it is relative velocity between the liquid and the particle, and option D, it is terminal velocity of a particle. So transition is happening from pneumatic transport to the transport line. Sorry. During transition of pneumatic transport fluidization, transport line is determined by what? So here it is superficial gas velocity is not playing a picture. Rather, relative velocity between gas and the particle plays a role. So option B is the right. Sorry. Option C is the option B is the right answer. So option B, that is the relative velocity between gas and the particle, is the right answer. So now we'll go to question 9. In question 9, it is given that it is a problem. UMF is the minimum fluidization velocity for the bed of particles, and increase in the superficial gas velocity from 2 UMF to 2.5 UMF results in dash, no change in. So here what is given, UMF is the minimum fluidization velocity for a bed of particles, that we know that UMF is the minimum fluidization velocity. So if we increase the superficial gas velocity from 2 UMF to 2.5 UMF, what are the parameters that remain unchanged? And here it is given that velocity is less than the entrainment velocity. Entrainment velocity is nothing but the velocity at which the particles will be escaping from the bed, or it will be moving out of the bed zone. And here it is, we are increasing the velocity to 2.2 to 2.5 times of UMF, so which would be remaining unchanged. First one, it is drag on particles. Option B, it is drag on column walls. Option C, it is bed height. Option D, it is bed voidage. So drag on particles, it would be changing because it has a direct influence from the velocity of the fluid, so it is will be varying. And second one is drag on column walls. Again, this depends on the fluid inlet velocity, and therefore drag on column walls would also be changing. So the C option is bed height. So once the bed reaches a certain portion, we are able to see that the bed height is constant beyond that, because however here we have crossed the minimum fluidization velocity, and we are finding out at which, or there would be no change when we increase the velocity from 2 to 2.4. So bed height is the correct answer where there is no change. And option D, it is bed voidage. Bed voidage again would be depending on the number of particles inside the system and the fluid. So answer is option C is the right answer. Sorry, bed height is the right answer. Option C is the right answer. I don't know why I have given all wrong answers. So option C is the right answer. Next is a problem. So first I'll read out the question and then we'll take 5 minutes break, and after coming back from the break we'll discuss the answer to that particular problem. Right? Alright. So we'll see the question first. Calculate the minimum bubbling velocity using Geldat and Abrahamson 1978 correlation for group A of particles 2.5 mm diameter. Air density is given as 1.2 kg per meter cube, and viscosity of air is given as 1.8 into 10 power minus 5 kg per meter second. And option A it is 0.55 meter per second. Option B it is 0.65 meter per second. Option C it is 0.25 meter per second. Option D it is 0.85 meter per second. So what is being asked in the question? We are asked to calculate for the minimum bubbling velocity when we are using Geldat and Abrahamson 1978 correlation for group A particles of size diameter 2.5 mm, and we are using the fluid medium as air, so it has density of 1.2 kg per meter cube and viscosity as 1.8 into 10 power minus 5 pascal second or kg per meter second, kg per meter second, kg second per meter, whatever it is. So now we need to find out the minimum bubbling velocity. So just try to solve this problem. And now the time is 3:45. We'll be back by 3:50. Okay, so we'll come back now. Here the question is about calculating the minimum fluid bubbling velocity using Gildart and Abrahams and 1978 correlation. So let us now see how to solve this, and for that we'll solve that. Excuse me. So for So first, I have been following this while taking the class. So first we'll write given. So this would help us identify what is given and what we need to find and what is the formula we need to be incorporating. So the first one is we need to calculate the minimum bubbling velocity using Gildart and Abraham correlation for group A particles of diameter 2.5 mm. So given is group A particles and diameter is 2.5 mm and air density is 1.2 kg per meter cube and viscosity is equal to 1.8 into 10 power minus 5 kg per meter second. So this is the given. Alright. Now we need to find this. Alright. We need to find minimum bubbling velocity. And formula is Gildart and Abrahamson 1978 correlation. So solution. First we need to identify Gildart and Abrahamson 1917 correlation. So do anyone of you want to give the Gildart and Abrahamson 1978 correlation? You can give, or else we'll solve the problem however. Okay, I'm just giving the formula myself. And for group A particles, it is important. MB is equal to 33. This formula we have seen in the previous text. Divided by symbol mu g. Point 1. This is the formula. So now we need to substitute everything back over here, and UMB is equal to 33 into 2.5 into 10 power minus 3 into rho g by mu g. What is rho g? Rho g is 1.2 divided by 1.8 into 10 power minus 5 into 10 power minus 5 and whole power 0.1. So now we need to calculate. So if anyone calculates, you can give the answer. First we'll find out what is in the bracket. 1.2 divided by 1.8 into 10 power 5, because it comes to the numerator, to the power of 0.1, and equal to 2.5 into 33 into 10 power minus 3. Answer is 0.2505 is the answer, and it is in meter per second. So we have found out the answer rightly as 0.25 meter per second. So C, option C is the right answer. So we'll look back the problem once again. So what is given? It is given that the particles are group A particles of diameter 2.5 mm, and we are using the air as a fluid, and its density is 1.2 kg per meter cube, and viscosity is 1.8 into 10 power minus 5 kg per meter square. And to find the minimum bubbling velocity, and the formula we are asked to use is Gellert and Abrahamson correlation. So the solution is that Gellert and Abrahamson correlation, first we need to find out for group A particles, and it is nothing but UMB is equal to 33 dp into rho g by mu g to the whole power of 0.1. So we are substituting all the known values in this particular formula, and we are getting the answer as 0.2505 meter per second. So here actually we can just so yeah, that is clear now. So I think question 11, it is about Reynolds number for particles in Stokes region. Reynolds number of particles for Stokes law region is REP is less than or equal to 0.1, and BREP is greater than equal to 1.0, and CREP is equal to 1, and DREP is less than 0.5. So what is Stokes regime? Stokes regime is nothing but when we have the laminar zone and we have the creeping flow kind of thing. So in Stokes region, since it is a laminar flow kind of thing, we know that it happens at a low velocity. So V should be very low, and if low velocity and laminar zone, we have Reynolds number also very low. So the low in the sense at what value? So Reynolds number less than or equal to 0.1 is the right answer. Option A is the right answer. Reynolds number less than or equal to 0.1 is the right answer, which corresponds to Stokes law region. So here in region where Reynolds number is less than or equal to 0.1, we know it is Stokes law regime, and the CD in this region is 24 by REP. So what is REP here? It is particle Reynolds number, and the formula for that is rho v dp by mu. Rho is the fluid velocity and u naught is the terminal velocity, velocity of the particles, or relative velocity between fluid and the particle, and dp and divided by mu. Dp is the diameter of the particle and mu is the viscosity of the fluid. So we should keep these things in mind. And we'll go to question 12. In question 12, it is asked that calculate the single particle velocity, settling velocity, according to Weber correlation in 1974, When transport condition is well satisfied, where grain size at 50% passing sieve is 2.3 mm with drag coefficient of 0.44. Density of particles in the liquid is given by 1500 and 2000 kg per meter cube respectively. So what is being asked? We are asked to find the single particle settling velocity. Single particle settling velocity. And which correlation are we supposed to use? We are supposed to use Weber correlation. And when the transport condition is well satisfied, where grain size is 50% passing 2.3, D50 here is 2.3 mm and drag coefficient is 0.44. Drag coefficient 0.44, what does it mean? It means it is in the turbulent regime. And the density of particle and liquid is given as 1500 and 1000 kg per meter. That is, liquid is water and particle is 1500. So now we'll see how to solve. Options are 0.1546 meter per second. Option B 0.1946 meter per second. Option C 0.1846 meter per second. Option D 0.1246 meter per second. So we'll solve this first. Question 12. Here the fluid is water, and from the question we'll just split what we need to find. Okay, we are asked to find single particle terminal velocity. And we are asked to use Weber 1974 correlation. What was given? dP50 is 2.3 mm. And density of particle is 1500 kg per meter cube. And density of water is 1000 kg per meter cube. And what else is given? CD is given 0.44. Yes, these are the things given. Now we need to use the Weber 1974 correlation. And do any one of you remember what is Weber 1974 correlation? For single particle settling, it is U, or else I'll just insert the equation and give you. Four into dP50 into rho P minus rho L rho P minus rho L into G divided by 3 rho L. So now we need to substitute things in this particular formula. Now we know it is 4. Sorry, here it is one more thing is missing. It is to the power of 1 by 2. So now we need to put everything. 4 into dp50 is 2.3 into 10 power minus 3 into rho p is 1500 minus 1000 into 9.81 divided by 3 into 0.44 into 1000. The power of 0.5. Now finding out the answer will be, we'll just calculate the answer. It is 4 into 2.3 into 10 power minus 3 because it is 2.3 mm into 1500 minus 1000 into 9.81 divided by 3 divided by CD, that is 0.44, and divided by rho L, that is 1000, and whole to the power of 0.5. We are getting 0.184849 meter per second. So we'll see if it is the right answer. Yeah, answer is right. It is 0.1846 meter per second, and we have got 0.1849 meter per second. So that is almost right. So how did we find out the answer? Let us go through the question once again and we'll see. So in question it is asked that we are asked to calculate the single particle settling velocity according to Weber correlation 1974 when the transport condition is well satisfied, where grain size at 50% passing is 2.3 mm with drag coefficient of 0.44. Density of particle and liquid is given by 1500 and 1000 kg per meter cube, and because of that, first we have written the given is nothing but the 50% passing diameter, that is dp50, that is 2.3 mm, and next is density of particle, that is 1500 kg per meter cube, and density of water, density of liquid, that is 1000 kg per meter cube, and we are asked to find a single particle settling velocity and by using Weber 1974 correlation. And Weber 1974 correlation is nothing but U set is equal to 4 into dp50 into rho p minus rho l into g by 3 cd into rho l whole to the power of 0.5. So we have substituted all the known things in the equation and we have got the answer as 0.1849 meter per second. So that is the right answer. And now we'll go to question 13. In question 13, okay. In question 13, what are we asked? Conveying of fine spherical particles as a suspension takes place in colloidal dispersive flow regime at what Reynolds number? So here we are conveying the finer size spherical particles as a suspension in a colloidal dispersive flow regime. So this takes place at Reynolds number of what? RES is nothing but Reynolds number of solids, that is REP or RES, whatever. And what at what condition conveying of fine solid spherical particles takes place? Fine spherical particles as a suspension takes place. So option A, it is RES is less than 10 power minus 5, and option B, RES is greater than 10 power minus 5. Option C, it is RES is less than 10 power minus 6, and option D, it is RES is greater than 10 power minus 6. So option 10 power minus 6, less than 10 power minus 6, I think. Option C. Yeah, option C is the right answer. That is RES or REP less than 10 power minus 6 is the right answer. So after that, question 14. In question 14, we are again, it is a problematic question, and in question 14 it is asked that air density 1.22 kg per meter cube and dynamic viscosity 1.9 into 10 power minus 5 kg per meter second, is flowing in a fixed bed of diameter 0.5 meter and height 2.5 meter. Bed is packed with spherical particles of diameter 10 mm. Void fraction is 0.38 and air mass flow rate is 0.5 kg per second, and calculate the pressure drop across the bed of particles. So we'll see how to do this. As always, question 14, answer. So what we'll be writing? We'll be writing the given first, and we need to find know what to find, and formula and the solution. This is the step we'll be using and we'll be following always. And in the first one, it is first given is fluid is air. So density is 1.22 kg per meter cube, and viscosity is given 1.9 into 10 power minus 5 kg per meter second. And what was given next is particle size or diameter. What is the particle diameter given? It is 10 mm and it is spherical, is equal to 10 mm sphericity. Since these particles are spherical, sphericity is 1. And what else is given? Density, viscosity, fixed bed of diameter 0.5 and a height 2.5. Bed diameter is equal to 0.5 meter and height 0.5 meter. And air mass flow rate is 0.5 kg per meter second. Flow rate is 0.5 kg per, and void fraction is equal to 0.38. So yeah, that's all is given. That's all given, and we need to find the pressure drop across the bed. And we need to find, we are using Ergun's equation. It is a packed bed and we are using Ergun's equation. So I have the formula over here. So I'm just copying it and pasting there. And now we are substituting it. Delta P is equal to pressure drop is equal to 150 into 1.9 into 10 power minus 5 minus 5 into okay, here we need to calculate something else. Before that, u naught we need to calculate, that is because here we are given only mass flow rate, so we need to find the u naught. So it is 0.5 kg per second divided by 1.22 kg per meter cube gives uh, meter cube per second, that is volumetric flow rate of air, divided by 1.22, and we need to divide it again by area. So what we are doing, we are dividing the mass flow rate into not into divided by density into CSA of bed. 0.5 divided by 1.2 into 3.14 into by r square. R is 0.25 square. So that's it. So u naught we are getting as 0.5 into 1 divided by 0.5 divided by 1.22 divided by 3.4 divided by 0.25 square. It is 1.9286 meter per second. So now here we have 150 into mu into u naught. U naught is 1.92, and into length of the bed it is 2.5 into epsilon is 1 minus 0.38 now divided by 1 square into dp is 2.5 into 10 power minus 3 whole square into epsilon cube into 0.38 cube plus again 1.75 into density is 1000 into u naught square 1.9286 square into 2.5 into 1 minus 0.38 divided by dp is 2.5 into 10 power minus 3 and into epsilon cube, that is 0.38 cube so this is thing. Now we need to find what is the value. 150 into 1.9 into 10 power minus 5 into 1.9286 into 2.5 into 0.62 square divided by 2.5 square divided by 10 power minus 6 divided by 0.38 cube. It is 15402.088 and the right hand side is 1.75 into 1000 into 1.9286 square into 2.5 into 0.62 divided by 2.5 divided by 0.38 cube. Okay, something went wrong again. I am just doing the U naught calculation. 0.5 divided by 1.22 divided by 3.14. Okay, here it is not 1.22, it is 2.088. 2.088, and again here it is 2.088. So here it is not the answer. 150 into 1.9 into 10 power minus 5 into why here it is something is missing. 150 into mu into u naught into lb. 1.9 into 10 power minus 5 into 0.62 square divided by 0.38 cube divided by 2.5 square. Okay, dp is not 2.5. Oh my goodness. It is. What is the diameter of the particle? It is 10 mm, not 2.5 mm. So again, 150 into 1.9 into 2.088 into 2.5 into 0.62 square into divided by 10 power minus 4 divided by 0.38 cube. And plus 1.75 into 1000 into 2.088 square into 2.5 into 0.62 divided by 10 power minus 2 into 0.38 cube. Again it is not 1000, it is 1.2. Did I do that? No. Okay. Answer is 26904.1 Pascal. 0.264 into 10 power 5 Pascal, or 26,904 Pascal. It is 0.264904 into 10 power 5 Pascal. So however we got the answer. So this is a straightforward problem. Here we are given air as a fluid, and I just messed up some places, that's why the confusion. But else we are using air as the particle, fluidizing medium, and its density and viscosity is given, and mass flow rate is given as 0.5, and particle density is 10 mm, and bed diameter is 0.5 meter, and height is 2.5 meter, and void fraction is given. So we are asked to find the pressure drop across the bed, and for that we are using Ergun's equation since it is a fixed bed, and LP is equal to 150 mu u naught LB into 1 minus epsilon square divided by 5 square dp square into epsilon cube, plus 1.75 into rho into u naught square LB into 1 minus epsilon divided by 5s dp into epsilon cube. So for the solution we are using u naught. First, we are finding U naught, which is mass flow rate divided by density into cross-sectional area of bed. And after that, we are substituting everything in the pressure drop. In question 15, it is asked that for solid liquid homogeneous flow regime, void fraction at minimum fluidization for spherical particles is, for solid liquid homogeneous flow regime, void fraction at minimum fluidization for spherical particles is option A 0.4 to 0.45, option B 0.5 to 0.58, option C 0.3 to 0.32, option D 0.15 to 0.25. So solid liquid flow homogeneous flow regime, void fraction at minimum fluidization for spherical particles is nothing but 0.4 to 0.45. So if we are using spherical particles and at the homogeneous solid liquid homogeneous flow regime, we have the void fraction as 0.4 to 0.45 at minimum fluidization condition. So that is question 15. In question 16, we have match the following, where RES is Reynolds number of solids and homogeneous flow regime. What is given in the left hand side? First we'll see homogeneous flow regime, pseudo homogeneous flow regime, and heterogeneous flow regime. And in the right hand side we have Reynolds number in the range of 0.1 to 2, and Reynolds number less than 0.1, and Reynolds number greater than 2. So first we'll see homogeneous flow regime. Homogeneous flow regime occurs when it is a very low Reynolds number, whereas in heterogeneous flow regime occurs when there is a very high Reynolds number. Because at a higher Reynolds number, we have the mix-up of this fluid and the solids, and bubble formation also will be there. So we call it a heterogeneous flow regime. So for homogeneous flow regime, Reynolds number should be very low. So the answer is Reynolds number less than or equal to 0.1. And heterogeneous flow regime, Reynolds number should be greater than 2. And for pseudo homogeneous flow regime, it should be in between, that is 0.1 to 2. So P is 2, Q is 1, R is 3. 2, 1, 3 is the right answer. We will see what the options are now and match. Option A P1, Q3 R2, option B P2 Q1 R3, option C P3 Q1 R2, option D P2 Q3 R1. So what was our answer? P2 Q1 R3. P2 Q1 R3. Option B is the right answer. So answer is option B. Because homogeneous flow regime occurs when there is a very low Reynolds number, and heterogeneous flow regime occurs when the Reynolds number is very high. Very high matlab it is greater than 2. And pseudo homogeneous flow regime occurs when the Reynolds number is between 0.1 to 2. So question 17. In question 17, which among the following fluidization regimes causes movement of solids to become more vigorous at a higher flow rate? Which among the following fluidization regimes causes movement of solids to become more vigorous at a higher flow rate? So the fluidization regimes, when we increase the flow rate, which causes the movement of solids to become more vigorous. So for that, option A bubbling fluidization, option B turbulent fluidization, option C slugging fluidization, option D fast fluidization. So option A bubbling fluidization is the right answer, because more vigorous with increasing velocity happens in bubbling fluidization, whereas these things are already existing in all other things. Only in bubbling fluidization we are able to observe the transition becoming more vigorous at a higher flow rate. So option A is the right answer. So question, okay. Till now we have seen about week 3 assignment problems. So now we'll just look at week 2 answers. That was this week's assignment problems. So we'll just see and discuss if anything needs to be discussed, and just, I mean, you people already would have submitted just for your revision. If you have any doubts in those problems, you can ask. So for that reason we are doing this. So question 1. At terminal velocity, the weight of the object is W is equal to buoyancy force plus drag force. Option B, W is greater than buoyancy force plus drag force. And W is less than buoyancy force plus drag force. And option D, none of the above. So at terminal velocity, the weight of the object is W is equal to buoyancy force plus drag force. Option A is the right answer. Because we have seen this in the last class itself, how the buoyancy force and the drag force is balanced from the weight of the particle, and therefore from that only we will be calculating the terminal velocity. So answer is option A. And question 2, it is about when the packed bed condition diminishes, frictional pressure drop can be estimated using Fick's law. Option B, Ergun equation. Option C, Stokes law. Option D, Newton's law. So this question also again we have seen, wherein we have used in today's class actually. Just a minute guys, I'll be back. Okay, so we have seen actually Ergun equation, how pressure drop can be estimated from the Ergun's equation when we are dealing with packed bed condition. So in option B is the right answer. So answer is option B, Ergun equation. So what is Ergun's equation? Ergun's equation is nothing but delta P is equal to 150 mu u naught into LB into 1 minus epsilon square divided by 5a square dp square into epsilon cube plus 1.75 into rho u naught square into LB into 1 minus epsilon divided by 5s dp epsilon cube. This is a formula we have used in today's class to get the pressure drop value. So when packed bed condition diminishes, frictional pressure drop can be estimated by using dash. So here we are using Ergun's equation. So Ergun's equation is nothing but pressure drop is equal to 150 mu u naught LB into 1 minus epsilon square divided by 5 square epsilon square cube dp square plus 1.75 into rho u naught square into LB into 1 minus epsilon divided by 5s dp epsilon cube. So here mu is the viscosity of fluid, u naught is the particle velocity, and LB is the length of the packed bed, and epsilon is the void fraction, and 1 minus epsilon is the volume fraction of solids, and phi s is the sphericity, and dp is the diameter of the particle, and that's it. So this is the formula guys. And now we'll go to question 13. In question 13 it is asked that for particles, spherical particles, minimum voidage of the bed usually is in the ranges of. So this question again we have seen today. So what is the answer? So it is 0.4 to 0.45 is the right answer. Option A is 0.4 to 0.45. Option B it is 0.5 to 0.55. Option C it is 0.6 to 0.65. Option D it is 0.7 to 0.75. So this is how the packing of solids looks like, and if we calculate we will be getting the void fraction as 0.4 to 0.45. That's right. So now we are going to question 4. Minimum fluidization velocity is affected by the following factors: bed diameter, particle size, and fluid density, all the above. So minimum fluidization velocity can be calculated from Ergun's equation if we speak retrospectively, and therefore if we get minimum fluidization velocity from the Ergun's equation, so what are the factors minimum fluidization velocity would be depending on. So first one is diameter of the bed. So obviously diameter of the bed, it is playing a role, because superficial gas velocity will be calculating from the flow rate and on that particular area, and particle size again is an important factor, dp, and fluid density is again important, we are using rho everywhere. So all the above is the right answer. So question answer to this particular question is an option D, all the above. So just give me 2 minutes, I'll be back. So we'll go to question 5. Okay, yeah, this is the formula. So all the above is the right answer. So in question 5, buoyancy force experienced by submerged particle is equivalent to option A, volume of fluid displaced by the particle volume into fluid density into gravitational acceleration. Option B, weight of fluid displaced by particle volume into fluid density into gravitational acceleration. Both A and B, none of the above. So buoyancy force, we have seen in previous things itself how it is calculated. It is nothing but the volume of the fluid displaced by the particle volume into fluid density into gravitational density. Option A is the right answer. Volume of fluid displaced by the particle volume into fluid density into gravitational acceleration. And question 6 we will see, it is at the minimum fluidization velocity inside a fluidized bed, all particles are suspended by upward flowing gas or liquid. Frictional force between particle and the fluid counterbalances the weight of the particle. Both A and B, none of the above. So what happens at minimum fluidization velocity? At minimum fluidization velocity, we know that the particles are loosely packed and it is nothing but all the particles are suspended by the upward flowing gas or liquid. And second one is frictional force between particle and the fluid counterbalances the weight of the particle. Again, this is true because at this condition, the weight of the particle just is counterbalanced by the frictional force between the particle and the fluid. So answer is both A and B is the right answer, option C. Now we'll go to question 7. Drag coefficient in the turbulent flow regime is equivalent to 0.44, and when the Reynolds number is, so option A greater than 500, option B greater than 1000, option C greater than 1500, option D greater than 2000. So here it is given that drag coefficient in turbulent flow regime is equivalent to 0.44. We know that CD is given separately for the Stokes regime and the turbulent regime separately. In Stokes regime, CD is equal to 24 by REP, and in turbulent regime, CD is equal to 0.44. So if 0.44, we know it is a turbulent regime. So turbulent regime, when does it happen? So when Reynolds number is greater than 500 or 1000 or 1500 or 2000. So we can say that when Reynolds number is greater than 500 itself, it is turbulent regime, and the drag coefficient is given by 0.44. So option A is the right answer. Now we will go to question 8. In question 8, it is given that at the onset of fluidization, the voidage is larger than in a packed bed, smaller than that in a packed bed, equivalent to that in a packed bed. Option D, none of the above. So this again we have seen, at the onset of fluidization, voidage is greater than that in the packed bed. Because packed bed, the particles are very tightly packed, so the voidage is very low. Whereas in fluidized beds, it is very high. But at the onset of fluidization or at the condition of minimum fluidization, we can say that it is larger than that in the packed bed but smaller than that in the fluidized bed. So it is option A is the right answer. And question 9, Archimedes number or Galileo number is proportional to this. Also it is like dp cube into rho p minus rho f into g divided by mu, something like that the Archimedes number comes. So exact formula is proportional to dp cube. So on looking at the options, I'm just looking at the exact formula. So Archimedes number is given by dp cube into rho p minus rho f into rho f into g divided by mu square. So it is proportional to dp cube, I mean cube of the diameter of the particle, and relative density between the particles in the fluid, and in the fluid density and the gravitational acceleration, and it is inversely proportional to the square of the viscosity of the fluid. So the question can be asked in any way, and you must be prepared to answer that in the any way. So answer option A is diameter of the particles, option B square of the diameter of the particles, option C cube of the diameter of the particles, and option D none of the above. So Archimedes number, as we have seen, that it is equal to rho p minus rho f into dp cube into g divided by mu square. So cube of the diameter of the particles is the right answer. So yeah, C is the right answer. Option C is the right answer. We'll now move on to question 10. In question 10, it is asked that at the minimum fluidized condition, the pressure drop through any section of the bed is equal to weight of the fluid in that particular section, weight of the particles in that section, weight of fluid and the particles in that section, and all the above. At minimum fluidized condition, pressure drop through any section is equal to weight of fluid and the particles in that section. Option C is the right answer. Now we'll go to question 11. In question 11, it is asked that gas holdup alpha G can be experimentally obtained by phase isolation technique, where alpha G is estimated by. So as we have seen in the last class itself, how it is estimated, alpha G, that is gas holdup, it is estimated by using phase isolation technique. And how exactly alpha G is calculated when we are using phase isolation technique? So alpha G can be estimated by the ratio of gas volume to mixture volume. Option B, ratio of liquid volume to the mixture volume. Option C, ratio of gas volume to liquid volume. Option D, none of the above. So gas holdup is nothing but alpha G. So it should be gas volume in the numerator. So, and in denominator it should be the entire volume On that basis, if we see, gas holdup can be defined as the ratio of gas volume to the entire mixture volume. So option A is the right answer. Ratio of gas volume to the mixture volume. And in question 12, moving on, we have that terminal velocity can be found from balancing the forces. This also we have seen in today's class. I think terminal velocity can be last class. Drag force and the weight of the buoyancy force is equal to W. If we put, we'll get the terminal velocity. So terminal velocity can be found from balancing the forces, gravitational and inertial forces per unit volume of the particle, gravitational, buoyancy and drag force per unit volume of the particle. Option C, gravitational and drag force per unit volume of the particle. Option D, none of the above. So right answer is we are balancing all the forces. So gravitational, buoyancy and drag force per unit volume of the particle is the right answer. Option B is the right answer. So gravitational, buoyancy and drag forces per unit volume of the particle is the right answer. So now let us move on to question 13. In question 13 it is given that for the flow of homogeneous mixture of gas and liquid, superficial liquid velocity can be calculated as volumetric flow rate of the liquid by cross-sectional area of the bed, volumetric flow rate of the liquid divided by half of the cross-sectional area of the bed. C. Volumetric flow rate of the liquid divided by square of the cross-sectional area of the bed, and none of the above. This question we have seen, and no, I mean we haven't exactly seen, but we have used in today's problem where we were finding U naught for estimating the pressure drop through the packed bed. So how did we find U naught? There U naught is equal to flow rate. It was given mass flow rate, so we divided by density to get the volumetric flow rate, and after that we divided by the cross sectional area of the column. So here it is, superficial liquid velocity is equal to flow rate, volumetric flow rate of the liquid divided by cross sectional area of the bed. So option A is the right answer. Volumetric flow rate of the liquid divided by cross sectional area of the bed is the right answer. Now we'll go to question 14. In question 14 it is asked that calculate the terminal velocity for the sharp irregular sand particles where density of gas is 1.2 into 10 power minus 3 gram per centimeter cube and viscosity is 1.8 into 10 power minus 4 gram per centimeter second. dP star is 160 micrometer and density of solid is 2.6 gram per centimeter cube and phi s is 0.67. And option A 88 centimeter per second, option B 66 centimeter per second, option C it is 77 centimeter per second, option D it is 55 centimeter per second. 88 is the answer actually. So we'll see how to solve that now. Yeah. I've already solved actually, so we'll just do it in our way. Okay. Given okay. So density of gas is 1.2 gram per centimeter cube. Viscosity is 1.8 into 10 power minus 4 gram per centimeter square. dP star is 160 micrometer. Density of solid is 2.6 gram per centimeter cube and pi s is 0.67. So it is in the laminar regime. So we to find UT. And first we are writing the formula. And by how are we doing? We are assuming laminar regime. and ut is equal to rho p minus rho f into g into phi s into dp square divided by 18 mu. So solution ut is equal to 2.6. Actually I don't want to go with this. Okay. I want to substitute it in 2600 minus 1.2 rho p minus rho f into g into phi s into dp square. Phi s is 0.67 into dp square dp square. dp is 160 micrometer, so 160 into 10 power minus 6 the whole square divided by 18 into 10 power minus 5. So it is 2600 minus 1.2 into 9.81 into 0.67 square into 160 square 10 power minus 12 1.8 to 10 power 5. It is not 0.9, it is 0.90 meter per second. In centimeter per second, it is 90 centimeter per second. So since we have made an assumption that verify our assumption, we are calculating Reynolds number. REP is equal to rho VdP by mu. So rho is 1.2 kg per meter cube into 0.90 and 1.16 into 10 power minus 6 into 10 power minus 5. 1.2 into 0.9 into 160 divided by 1.8. 9.6 we are getting, so it is close enough and therefore our assumption is right. So 90 centimeter or 88 centimeter per second is the right answer. So that is question 14, and now we will go to question 15. 5 more questions and we are done for the day. So in question 15 it is asked that according to Venn and U 1966, a void fraction of the minimum fluidization epsilon mf depends on density of the particles, shape of the particles and volume of the particles, none of the above. So in last class itself we have seen how phi square epsilon mf cube is equal to, I mean not equal to but approximately equal to 1 by 14, or epsilon mf cube is approximately is equal to 1 by 14 phi s square, and epsilon mf is inversely proportional to 1 by, I mean inversely proportional to the sphericity of the particle. So according to Venn and U 1966, a void fraction at minimum fluidization depends on phi s. What is phi s? Phi s is the sphericity of the particles. So sphericity denotes the shape of the particles. So option A, density of the particles is false. Option B, shape of the particles is true. And option C, volume of the particles is again false. Void fraction at the minimum fluidization depends on shape of the particles according to Venn and U. It is not according to anyone else. So it is according to Venn and U. If it is like general question, shape might not be as effective answer, but according to Venn and U, it depends on shape of the particles. So that is question 15. In question 16, we are finding that drag force is acting in which direction to the relative motion of any object moving with respect to a surrounding fluid. So option A, same direction. Option B, opposite direction. Option C, either A or B. Option D, none of the above. So again, this question we have seen in last class, how drag force acts in the opposite direction to the relative motion of any object. So if it is it is like acting relative opposite to the relative motion of any object. So option B is the right answer. Option B is the right answer. So here we are stating that drag force is acting in opposite direction to the relative motion of any object moving with respect to the surrounding fluid. So if um, like consider a particle falling down in a fluid, so drag force would be acting upward, that is pulling the particle up rather than falling down, so that is opposite direction. And so we go on to question 17. In question 17 it is asked that when the particle Reynolds number value is 680, the flow is Stokes flow, laminar flow, turbulent flow, all the above. So here Reynolds number is very high, so we can say that it is turbulent flow. Turbulent flow is the right answer. And question 18, at minimum fluidization velocity, weight of the particle is just counterbalanced by the frictional force between the particle and the fluid, gravitation force acting on the particle, buoyancy force acting on the particle, none of the above. So weight of the particle is the gravitational pull acting on the particle. How it is counterbalanced? It is counterbalanced by the frictional force between the particle and the fluid. So option A is the right answer. We'll go to question 19. In question 19, distributor hole diameter, it is that distributor is nothing but through which the air passes. So distributor hole diameter affects the flow minimum fluidization velocity, categorized as thermodynamic variable, geometric variable, variables as physical property, none of the above. So distributor hole property is classified as geometric variable because it is a property of the geometry of the system. So it is geometric variable. Option B is the right answer. Now we'll go to question 20. In question 20, fluidized bed is operating with air at minimum fluidized condition with particles of cubes 0.02 meter. Calculate the void fraction of the bed. Okay. Okay. So here it is given that cubes of size 0.02 meter is used and we have to find the void fraction of the bed. So option A 0.45, option B 0.35, option C 0.25, option D 0.55. So how will we calculate this? Sorry, 1 divided by 0.81 square divided by 40 power 1 divided by 3. What did Brennan use? Calculation used. They used they gave a correlation to find the epsilon mf at minimum fluidization condition. Okay, it is not phi square actually. I have been saying when a new correlation uses epsilon mf cube is inversely proportional to phi s, not phi s square. I have been saying that wrong in the past question. So now we'll find out answer. Question 20 answer. First it is given to find and form. So given cube side is 0.02 meter and to find void fraction. And formula, insert equation. First we need to find phi s. Phi s is sphericity. So volume of cube is 0.02 cube is 8 into 10 power minus 6 meter cube. All right. Now surface area of cube is equal to 6 into a square. 6 into a square is equal to 6 into 0.02 into 0.02. Now volume of sphere is equal to this. If volume of sphere is equal to this, dp is equal to pi by 6 dp cube is equal to 8. So this one 8 into 10 power minus 6 pi by 6 dp cube is equal to 6 divided by 3.14 pi by 6 dp cube and divided by 3. Again this dp is equal to this. Surface area of sphere is pi r square is area of circle 4 pi r square pi d square. So it is 3.14 into dp square. So we'll get this. Insert symbol. It is where is pi. Symbol pi. Insert close pi by 6 dp cube. Pi dp square is equal to 3.14 into this. So first we will calculate 6a square. 6 into 0.02 square is equal to 2.4 into 10 power minus 3 and pi by 6 dp cube 8 into 10 power minus 6 into 6 divided by pi into 6 divided by pi power 1 divided by 3. 0.0248 0.0248 square equal to into 3.14 1.933 into 10 power minus 3 meter cube meter square. meter cube, meter. Okay, now sphericity. Sphericity, sphericity is equal to surface area of sphere divided by this one. So what does it give? 1.933 divided by 2.4. It should be 0.805. Yeah. We all know the sphericity of cube is 0.81, right? So here that is what we got. Now we need to find epsilon mf cube is equal to 1 divided by 14 into 0.81 is equal to 14 into 0.81, 1 divided by answer 0.088, and epsilon mf is equal to power 1, answer power 1 divided by 3. So it is 0.445 or 0.45, whatever it is. So that is how we get the answer. So it is 0.45 is the right answer. So yeah, I think that's all for today's class. So if you have any doubts, we can discuss or else we can leave. Thank you.